We're the Sensing Verticality of Taut cable team, and we basically have two words to say about our project. We did it. We said we would design something, and we designed it. We said we would build something, we built it. We said we would test it, and we tested it. And this is what we tested. So as you can see, it's the SVCTM affixed to a scaffold there, being held by the robot arm with a cable going down the center. And as we're moving it about, the cable is taut. It's fixed at a set point in the bottom on the floor. So it's moving the little U-bars around, which the encoders are picking up. So when we tested it, we found we had an average error of about 0.4466 degrees. But we noticed during our testing that since we had decided to 3D print these parts for time and money's sake, they got caught a bit and there was a bit of a deadband issue. So we used a state-of-the-art component called tape, and we just taped around a bit, taped around here, and we found it slices the error roughly in half to about 0.26 degrees. So we think we can find ways to further improve, find ways to lower the deadband. We're just going to get more and more accuracy. This is our testing apparatus. In orange is the robot arm. It's what holds up everything. It's being moved by a remote, and we can move it very precisely so we know exactly where we're holding it in three-dimensional space. The robot arm holds up the SVTCM along with the scaffold system that we modified. And finally, you have the black taut cable going down the center, running through the SVCTM's U-joints.
Okay, now coming to the electronics part of it, we have two encoders mounted on the SVTCM. That's basically these ones. These are 13-bit SSI interface binary encoders. We have an Arduino board here to read the data out. It's done by bit banging. So you process a clock signal and read out every bit at a time. This is a code which pretty much reads the data and then gives us 4 values. Encoder value, that's a binary value that you have. The corresponding angle to it in terms of 360 degrees. And the same thing for the second encoder. So the testing procedure that we had was the robotic arm, or the SVTCM was mounted onto the robotic arm. And we moved it in one direction, either in the x-axis or the y-axis by a known value, through which we calculated known theta. And then we measured that with the known, with the encoder values that we get. And this is how we calculated our results.
So the proto to our design was the delta arm, which was made last semester, I believe. And we were tasked with improving on this design. It originally had 3 encoders, which is one more than you need. Our design only uses 2. It was a little flimsy, jumped up and down like a kangaroo, and it cannot be attached to the gantry. So going through our design process quickly, we came up with 3 rough ideas, alpha, beta, and gamma, which was a composition of a collet, 2 collets, or using a kind of a joystick system. In the end, we decided to go with designing gamma, and here is the SolidWorks style we made. And we were pretty pleased with it. We were about to start building it, but we decided to go back, spend a bit more time, and make the Gamma Design S, which is made of simplified parts and it makes manufacturing it a whole lot easier. On top of that, it's more steady, it's more stable when you're testing it, moving cable around. And we had to rebrand it after we finished it, the SVTCM, Sensing Verticality of Taut Cable Mechanism, and that's what you're seeing in front of you today.
So there's a few things that we want to do differently, or we'd like to improve on the design. The first is to use stiffer U-bars. It was actually kind of a source of error. We can pass these around afterward, but the original design called for using aluminum bars, but because of the tolerances and how high they need to be, they're much more expensive to make than we would have thought. So to do the testing, we had them 3D printed, and the result is that they're a lot more flexible than what you'd expect, and so when you're moving the cable around, they tend to get bound up with the bearing blocks that we have, just because they're not the best bearing blocks you can get. And when that happens, the flexure actually can throw off a lot of the data. It's a source of error. A second problem that we had was with the the scaffold itself, it's a little bit rickety, and so there's the potential for it to move around and twist a little bit, which can be another source of error. You can that demonstrates a little bit of it. When it does shift a little bit, and when you're trying to get to accuracies of 0.3 degrees and lower, that little bit of shifting, which is obviously exaggerated, it actually can throw off the data quite a bit. And the last thing we would probably do is to CNC the entire thing, just because when we're building it by hand, you can get very accurate, but just trying to position the bearing blocks, if they're off by just a little tiny bit, their perpendicularity to each other gets completely thrown off, which can introduce further errors.
All right. We'll be taking your questions now.
Great. Would you go back to the slide that shows your geometry for determining theta? It is a horizontal motion, and then there we go. So, given that this is your test, why did you just put this onto the table of a mill where you have reliable, straightforward, two-axis motion with excellent readouts, and test early and often and without that concern for the motion of the angle that may come from the arm?
The angle, that motion, that angle was probably could have been animated a little bit better. That's actually coming from it's from our fixation system. Not the arm itself does not twist around very much. It's actually this mechanism we have to mount the thing to the arm, that's what moves around. So putting on the mill, we still have a similar problem just because of the fixturing mechanism that we're using. The other issue with the mill for us was just the clearance between the top of the mill and the bottom. We wanted to have a little bit more space to work with. And otherwise we knew that we had access to the arm, so we wanted to use it.
Do you recall the intended accuracy that you advertised in September?
We said we will have it within 0.3 degrees of accuracy, and we still feel that we can achieve that if we can eliminate out the dead band and replace these components with aluminium and make it more stiffer there. So you eliminate a dead band there.
Right.
Where did the 0.3 degrees come from?
That was just a design requirement.
That was
So that was given to you.
yeah.
I had another question though. You said that making those hoops out of aluminum was too expensive. How expensive was it?
To 3D or to they have to be CNC'd for one because of the tolerances, and to bend them, I believe we need 4 to be made. It ended up being $500 the first time around.
$300 to $500 haven't made, and we had all these CNC
Like
like 100.
or 3D printed for about.
It's 3D printed about 100.
Is it necessary for those to be round, or could they be like water jetted out of a plate?
You could, yeah,
Did you explore that option?
a little bit. But once we had the bars or the mechanisms to attach it to the rotating shafts built already, so it was just easier to 3D print them.
How did this accuracy compare to the original prototype that you mentioned?
We tried running some tests on the original prototype, but we weren't able to get sufficient data to draw a conclusion with its accuracy.
You, these are style points. When you mentioned the S version, the creation of the S version, you referred to it as manufacturing. That ordinarily pertains when you're set up with a lot of fixturing and you're making a lot of them.
Should say machability.
Yeah,
Small scale manufacturing.
Verification.
Yeah, and what's the difference between this being flimsy and kind of flimsy?
Nothing.
What's the difference between the source of error and kind of the source of error? That was in verbal presentation on the slides.
Nothing discernible.
Sure. The others? Great. Thank you so